In this video, we will learn how to find confidence intervals, which means interval estimates for the population mean, using large samples. Large samples means samples of size n greater than or equal to 30. So for example, in a random sample of 35 soda and energy drinks, the mean sugar content was 30.5 grams with a standard deviation of 5.2 grams. Construct a 96% confidence interval for the population mean. The first thing to do in any problem is to identify the variables. So 35 in this problem refers to the sample size, which is n. 30.5, the mean sugar content, refers to x bar because it comes from a sample. S is the standard deviation, which is given to be 5.2 grams. And 96% refers to the confidence level, which is denoted as C. So C is 0.96 or 96%. So there are three steps to follow in this problem. The first step is to find the critical value ZC for a 96% confidence interval. The second step is the margin of error E, and the third is the confidence interval itself. So first, let's find the critical values, which are minus ZC and plus ZC for a 96% confidence interval. Now note that by the central limit theorem, we know that if samples of size n greater than or equal to 30 are repeatedly drawn from a population, the sampling distribution of the sample means, which is x bar, is normal. So it makes sense for us to work with a standard normal. So I will draw a standard normal and label the important points. The mean, so this is the standard normal. The mean of the standard normal is 0. And the first standard deviation mark is at 1. On this side it's minus 1. The second standard deviation mark is at 2. And on this side it's at negative 2, and so on. So the standard normal pretty much refers to the z-scores of the sample means, x bars. Now, what do we mean by 96% confidence level, right? So 96% refers to the area between minus ZC, the critical values, minus ZC and plus ZC that we are just about to find. So we want to find minus ZC and plus ZC so that 96% of the area is between these two values. So this area in the middle of minus ZC and plus ZC is 96%. And we want to find the minus ZC and ZC that would give us that area. The reason is because 96% confidence means that we want we want the confidence interval so that 96% of the sample means that you choose fall in this interval from minus ZC to ZC. That means the z-scores of those sample means fall in this interval. So you want to be 96% confident that if you pick a sample of size n greater than or equal to 30, its sample mean or its z-score of the sample mean is going to fall between the minus ZC and the plus ZC. So how do we find the minus ZC and the plus ZC? We know that there's a total area of 100% under the standard normal, and so we can find how much area is in the two tails, on the left tail and the right tail. The reason we need to do that is because the standard normal only gives us areas to the left, and so it is important for us to know particularly what is the area in the left tail of this graph. So the total area is 100% or 1, and from that we take away 96% or 0.96 and divide it equally into the two tails, the left tail and the right tail. So that gives us 0.04 divided by 2, which is 0.02. So this means that there is 2% or 0.02 of the area in each tail. So now if you looked up an area of 0.02 in the standard normal table, you can find what the minus ZC value is. Note that why have I drawn minus ZC or marked minus ZC and plus ZC beyond the second standard deviation mark? Because we know that in any standard normal or in any normal distribution, 95% of the area falls within 2 standard deviations. And we want 96% of the area, so it has to go, the ZC and minus ZC have to go beyond the second standard deviation mark. So now let's bring up the standard normal table, and we will try to locate an area of 0.02 in this table. Notice that 0.02 is approximately between 0.0197 and 0.0202, but it is closer to 0.0202. So correct to 2 decimal places, our ZC minus ZC value will be minus 2.05. So we can note that down in our graph. So minus ZC is minus 2.05, and so plus ZC is 2.05. So that is the first step in this problem. Now the next step is to compute the margin of error. There is a formula to compute the margin of error. So step 2, the margin of error, which we denote as E, is given to be ZC sigma over square root of n. Now, what does this mean? The margin of error means it is the maximum possible distance from the point estimate, which means from the sample mean, to the actual value of the population mean. So that's the maximum possible error, in other words. And the way you compute that is ZC sigma over square root of n. Now, sigma is the population standard deviation, and often it's the case that you don't know the population standard deviation. So because we are working with samples of size n greater than or equal to 30, we can replace the sigma by s that we know from our sample. So now we can compute this. ZC, as we just found out, is 2.05. S, the sample standard deviation, was given to be 5.2 in this problem. And we divide this by square root of the sample size, which is 35. And we can use a simple calculator to do that. So let's try to calculate 2.05, that is ZC, times the standard deviation 5.2, divide by square root of n, which is 35. And we get 1.801, etc. Now, depending on how many digits you need to round up, accordingly you will choose the decimal places. So up to 2 decimal places it would be 1.80, up to 1 decimal place it's 1.8, and we will just consider 1 decimal place. So going back to our document, our example, our answer is 1.8, correct to 1 decimal place. So that is the margin of error. And now the last step is easy. The 96% confidence interval for the mean for the population mean, mu, is given by the formula x bar, your sample mean that's given, minus the error that you just found, the margin of error. So x bar minus e to x bar plus e. So this is the confidence interval. And that's quite easy to calculate now since we have all the numbers. X bar is given to be 30.5 if I remember correctly, yes, 30.5, and the error that we just found is 1.8, so 30.5 minus 1.8 and 30.5 plus 1.8. So this is equal to, if we go back to a calculator, we can easily get that. So 30.5, let me just, .5 minus 1.8 is 28.7, and 30.5 plus 1.8 30.5 plus 1.8 is 32.3. So 28.7 and 32.3. Okay, so our interval is 28.7 to 32.3. And now we can interpret what this means. So this means that we are 96% confident that the actual value of the population mean sugar content in sodas and energy drinks is between 28.7 grams and 32.3 grams. And that completes the example. So we can say, just to write what I just said, so we can say with 96% confidence that the population mean sugar content in sodas and energy drinks is between 28.7 grams and 32.3